Griffiths, E&M, section 1.3.4, the fundamental theorem for divergences. So like we had a fundamental theorem for gradients, we also have a fundamental theorem for divergences. That fundamental theorem states that if I add up for a volume the divergence of some vector field over that entire volume, that equals the integral of the surface where that vector field lives. Okay, so let's try to conceptualize what that would mean. All right, the del dot v, all right, this divergence talks about the accumulation or inducing of flow, right? In my example of fluid flow, all right. So if I add up all of the flow, either coming into or out of a volume, that is equal to all of the streamlines of that flow, or the field lines, that are perpendicular to that surface containing that flow. All right, so here's some surface, right? My dA is some patch, some infinitesimal patch on that surface. dA points perpendicular to that surface, and v dot dA is going to capture all of the field lines that are leaving perpendicular to that surface. All right, so while this is dA on some edge, and maybe at that point I have some field line that looks like this, some vector field, right? The cosine, that this dot product picks out the component normal to that surface, picks out this component. This is v dot dA. This is commonly referred to as Gauss's theorem or Green's theorem or the divergence theorem. And the fact that this has so many names for it kind of suggests how important this is to E&M. All right. So let's go ahead and test this with example 1.10. We have some vector field V. Let's use black. That vector field is y squared x hat plus 2xy plus z squared in the y hat direction plus 2yz in the z hat direction. Okay, and I want to test this for some volume and some that is bounded by some area. Okay, so the simplest thing to do is to pick something you know the functional form for, and we're going to pick a cube. Okay, that's going to be the easiest thing to do. Okay, so there's my cube. We're going to say that cube has side length of 1. All right, so this is x, y, and z. All sides have length 1. All right, so let's go ahead and do the left part of this fundamental theorem for divergence. To do that, I first need to calculate the divergence of this vector field. That divergence of this vector field gives me, let's see, so I have dx in the x hat plus dy in the y hat plus dz in the z hat, dotted with this v vector. All right, I won't write that again. The x hat components combine. The partial of y squared with respect to x is 0, so there's nothing component coming from the x hat direction. The partial with respect to y in the y hat will be this piece right there, so that's going to be plus 2x. And the partial with respect to z of the z hat direction is going to be plus 2y. Okay, so that's our divergence, and then we need to integrate this over the volume. So we know that the volume for this sphere, or for this cube, goes from 0, 0, 0 to 1, 1, 1 of 2, I'll pull that 2 out, x plus y. And that infinitesimal volume element is the product of those infinitesimal lengths, dx, dy, dz. All right, the z1 is easy. I get 2 times 1. Then I'm left with 1/2 x squared plus 1/2 y squared evaluated from 0 to 1. And that should give me 2. 1/2 plus 1/2. Oh, I'm missing a plus sign. There you go. I did that integral very sloppily, so I'm going to just restart this. Okay, so I get 2 times 1. Then I'm left with the integral from 0 to 1 of x plus y. That's 1/2 x squared plus xy evaluated from 0 to 1. And then we're left with a dy still. So that becomes 2, 0 to 1 of 1/2 plus y dy, 2, 0 to, do the integral now, 1/2 y plus 1/2 y squared from 0 to 1. That becomes 1/2 plus 1/2. It's 1, so that becomes 2. Okay, I feel better about the way I did that there. So we know that the left side of this expression up top is 2 for this field and this shape. So now what we need to do is we need to evaluate the field lines leaving perpendicular to all of our surfaces. All right, and for a cube, we have 6 of them. I will evaluate a few of those for us. Okay, so let's go ahead and evaluate this surface first. Okay, we know what V is, and we need to determine what our infinitesimal area element is. Okay, so dA for this piece right here, that patch exists in the YZ plane, so that is going to be dy dz, right? Traversing this patch will be changes in y and z, but not x. And the direction is normal to this plane, and it should face out of our closed surface. So that means that that should point in the x hat direction, or out here. So I take this integral of v dot dA for this patch. This x hat component picks up the y squared, and we're left with this surface integral over y squared dy dz. Okay, so we have to figure out what our bounds are here. For dy, it's going to be from 0 to 1, and for dz, it's also from 0 to 1. 0 to 1, 0 to 1, y squared dy dz. All right, the z is just 1. Then I'm left with 1/3 y cubed from 0 to 1, and I'm left with 1/3. Okay, so let's go ahead and do another side. Your book picks this back side to be side 2, so I'll do that. That back patch right there. I go ahead and take v dot dA Now dA here is still in the yz plane, so dy dz, except now the vector that points outwards is now in the minus x hat direction. So we take that that component for our dot product here, and we're left with minus 0 to 1, 0 to 1, y squared dy dz, which is exactly what we had here, but it's in the opposite direction, this minus sign. So we know that the answer is going to be minus 1/3. Right. So far we've only done 2 of the sides. You have to do the remaining 4 before you can officially close your integral, right? This fundamental theorem is for a closed surface. So you need to do all of the surfaces to close that cube, and I'll let you do that on your own. But in the end, what should you get for the total integral over all of the surface of this field? What should you get?